A knowledge of the electronic configuration of atoms is vital for the understanding of the nature of the chemical bond. Each electron around the nucleus of an atom is in a specific orbital around the nucleus associated with a unique energy level. An orbital can be defined as a three-dimensional space around the nucleus where there is a high probability of finding the electron. The electronic configuration or energy of a particular electron around a nucleus is defined by a set of four quantum numbers. 1. Principal quantum number n determines the average distance of the electron from the nucleus and determines its principal energy level. N can have positive values 1, 2, 3, etc. The value of n also indicates the relative volume of the atom. 2. Azimuthal quantum number L determines the shape of the orbital with a given principal quantum number n. L can have only certain discrete values corresponding to orbitals of specific shapes. L can have values from 0 to n-1. 3. Magnetic quantum number m sub L determines the direction, that is, the relative orientation of the orbital in space. M sub L also predicts the number of orbitals possible with a specific L. M sub L can have integer values from negative L to positive L. 4. Spin quantum number m sub s determines the number of electrons in an orbital. An orbital can have a maximum of only 2 electrons. When there are 2 electrons in an orbital, they must have opposite spins. M sub s can have values of either positive half or negative half. Writing electronic configuration of atoms. For historical reasons, when writing electronic configuration, we combine the quantum numbers L and m sub L and indicate it by a letter. The table below gives their relationship. We know n predicts the volume of the orbital. N has values 1, 2, 3, etc. L predicts the shape of the orbital. L has values from 0 to n-1. M sub L predicts the number of orbitals and their relative orientation. M sub L has integer values from negative L to positive L. When n is equal to 1, L will be equal to 0 and m sub L will be equal to 0. The quantum numbers L and m sub L together represent one spherical orbital indicated by the letter S. When n is equal to 2, L can take values 0 and 1. When L is equal to 0, m sub L will be equal to 0. When L is equal to 1, m sub L can take values negative 1, 0 and positive 1. The quantum numbers L and m sub L together represent 3 dumbbell-shaped orbitals indicated by the letters px, py and pz. When n is equal to 3, L can take values 0, 1 and 2. When L is equal to 0, M sub L will be equal to 0. When L is equal to 1, M sub L can take values negative 1, 0 and positive 1. The quantum numbers L and M sub L together represent 5 variously shaped orbitals indicated by the letter D. Using the 4 quantum numbers, the electronic configuration of hydrogen is written as 1s1. In hydrogen, the superscript 1 over the letter S is the number of electrons in the s orbital. S describes the shape and the direction of the orbital that the electron occupies. The number 1 is the principal quantum number. In helium, the next electron also enters the 1s orbital. Its electronic configuration will be 1s2. The two electrons in helium must have opposite spins, since no two electrons can have the same set of 4 quantum numbers as per Pauli exclusion principle. The s orbital is now full. For building up of atoms' electronic configuration, electrons are added to various orbitals in the order of their increasing energy. The closer an orbital is to the nucleus, the lower its energy will be. Atomic orbitals' relative energies are: 1s orbital is less in energy compared to 2s, which is less in energy compared to 2p, which is less in energy compared to 3s, which is less in energy compared to 3p, etc. Outer electron configuration of elements in period 2. Period 2 elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. The next electron enters the higher energy 2s orbital in lithium. The outer electronic configuration of lithium will be 2s1. The full electronic configuration of lithium will be 1s2, 2s1. The next electron enters beryllium. The outer electronic configuration of beryllium will be 2s2. The full electronic configuration of beryllium will be 1s2, 2s2. Outer electron configuration of elements in period 2. Principal quantum number 2 allows values 0 and 1 for quantum number L. L equal to 0 corresponds to 2s orbital. With L equal to 1, 3 orbitals known as p orbitals are possible, since m sub L can have values negative 1, 0 and positive 1. The 3 p orbitals px, py and pz are dumbbell shaped, have the same energy and are mutually perpendicular to each other. The next 3 electrons enter successively the 2px orbital in boron, the 2py orbital in carbon, and the 2pz orbital in nitrogen. As per HUND'S rule, when there are degenerate orbitals, an electron will occupy an empty orbital before it will pair up. From oxygen, the entering electrons begins to pair up in the p orbitals. With neon, all p orbitals are full and it has a noble gas configuration having an octet of electrons. Such octet configurations confer extreme stability on the element. Hence, neon is a very unreactive element. Outer electron configuration of elements in period 3. Period 3 has elements sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. The next electron enters the 3s orbital in sodium with principal count number 3, coinciding with the start of the period 3 of the periodic table. The building up of the rest of the period 3 is very similar to the one for period 2. This period ends with argon having an octet configuration, and argon, like helium and neon, is an inert element. We see that elements in group 8A have similar properties, in the sense they are all chemically inert. We now begin to see how electronic configuration affects an element's behavior, most importantly its chemical reactivity. Since the properties of elements are determined in a large measure by their outermost electrons, the periodicity of properties stems naturally from the quantum mechanical rules and restrictions that determine the outer electron configuration of atoms. With the transition metal scandium, the 3d orbitals begin to fill. When n is equal to 3, L can have values 0, 1 and 2. When L is equal to 2, M sub all can have 5 possible values of -2, -1, 0, +1 and +2. Thus we have 5 d orbitals and each can accommodate 2 electrons. With inner transition element cerium, the f orbital begins to fill. In organic chemistry, we will be primarily dealing with the first 3 periods of the main group elements. Pauli exclusion principle and HUND'S rule in writing orbital diagrams. Orbital diagrams are written to indicate the relative energy levels of all electrons in an atom using 2 key quantum mechanics rules. The Pauli exclusion principle states that no 2 electrons in an atom can have the same set of 4 quantum numbers. The HUND'S rule states that the lowest energy arrangement for electrons in a subshell is obtained by putting electrons in separate orbitals of the subshell with a spin in the same direction before pairing electrons. In carbon, the 1s orbital will be filled first with 2 electrons having opposite spins as per Pauli exclusion principle. Then the higher energy 2s orbital is filled with 2 electrons having opposite spins. The next 2 electrons would go into 2 separate p orbitals with a spin in the same direction as per HUND'S rule. In nitrogen, each of the 3 p orbitals will have 1 electron each with spin in the same direction as per HUND'S rule. From oxygen, electrons would begin to pair up in the p orbitals.